Okay, let's start. Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh, and very good morning. So we will continue our class, which we are currently in chapter 2, the final subtopic of chapter 2, which is planar kinetics, force and acceleration, and the last subtopic is the general plane motion. So I have one more example that I would like to share with you today regarding the general plane motion in this chapter before we go into the third chapter of dynamics lah. So before we go into the example problem, let's recap what we have learned in this final subtopic, which is general plane motion for force and acceleration. So basically, you have three um, formulas that you need to know in order for you to solve problems in general plane motion. First of all, the coordinate system that we are using in this problem is the XY coordinate system, uh, which is not similar with the rotation problem where you need to use the normal and tangential axis. For this is the normal XY coordinate system lah, okay, for general plane motion. That is number one. And then the equations that you need to use to solve problem is, the first one is total force in x-axis equal to MAX. And then we have total force in y-axis is equal to MAY. And then we have the calculation of moment. You can calculate the moment about center of gravity, mg, which is equal to IG times alpha. This is one. You can also calculate moment about the IC point. So let's take, for example, if we have a wheel, like what we have calculated in the previous class. So the wheel is currently rolling on the ground. So in this case, the contact point between the wheel and the ground is the location of IC only and only if this is only the case when the wheel rolls without slipping. Rolls without slipping. Okay. So if the wheel rolls without slipping, then the contact point between the wheel and the ground has zero velocity, which means that in this particular location, V is equal to 0. V of that point is equal to 0. So that point is called the instantaneous center of zero velocity, IC. So we can also calculate the moment about IC. I put or here, MIC, which is then equal to IC times alpha. Okay, so one of the advantage of calculating the moment about IC is that you can eliminate unknown, such as the friction force. For example, if the coefficient of friction is not given, then you can eliminate the friction force by calculating the moment about IC. And for this, you need to get the IIC. This is standard that we need to use the parallel axis theorem. Okay, parallel axis theorem to calculate IIC, which is given by IIC is equal to IG plus md square, where d is basically the distance between IC and point G. That is the parallel axis theorem. And if it rolls without slipping, in the case where rolls without slipping only, then we have another equation that we can apply, which is AX is equal to alpha times R. This is the case only when rolls without slipping. Okay, only for the case of rolling without slipping. This only. If slipping occur, then we cannot use this. So if slipping occur, then we cannot use, then AX is not equal to alpha R. So what you can use is basically, therefore you need to use the friction calculation, the friction formula, which is FR friction is equal to mu K times the normal force, okay, times NA. So this is basically what you need to know for the general plane motion in this subtopic lah. Okay, so we have three equations. The moment equation can be calculated about G or about the IC. Point G is basically here at the center of gravity, the middle of the wheel. Point IC is at the contact point, given the wheel rolls without slipping. If the wheel slips, then you cannot use IC. That point is not IC. And if rolls without slipping, you have another equation, AX equals to alpha R. If slipping occur, then the equation cannot be used anymore. Okay, so let's move on to one more question or problem before we go into a new chapter. Okay, let's read the question first. 75 kg wheel has a radius of gyration. Okay, so you should notice that in this question, radius of gyration is given, which is 375 millimeters. So definitely we know that this is a non-homogeneous object. If it is subjected to a torque, okay, now you can see the word used here is a torque, and it is given M equals to 150 Newton meter. So like I said in the previous class, the moment applied to the object, it can be written as a couple moment. It can also be written as a torque. So this is basically a moment that is applied to the object. A moment is also a force, but it is not a linear force. It is a rotational force. Okay, a rotational force which, when this kind of rotational force is applied to an object, the object will start to rotate. Okay, so what you need to determine is its angular acceleration. Okay, so we want to calculate the alpha of this wheel, and then the coefficient of static and kinetic friction between the wheel and the grounds and the ground are mu s 0.2, mu k 0.15. Okay, this is the difference between this problem, this question, and the previous question that we have calculated. Okay, now let me ask you, is this problem the wheel rolls without slipping, or the wheel slips as it rolls? Which one? Who can answer that? Do you think that the wheel
without slipping
rolls without slipping, ataupun dia slips as it rolls?
without slipping.
Okay, Shamil said rolls without sleeping. What about the rest? How do you know that it is rolling without sleeping?
Sebab ada coefficient of kinetic friction.
Okay. Okay, let us zoom in to here. Do you understand what is the difference between coefficient of static friction and coefficient of kinetic friction? Why there are two coefficient of friction given? Mu s is the coefficient of static friction. Mu k is the coefficient of kinetic friction. So what is the difference? These two are coefficient of friction. These are coefficient of friction. Okay, why two types of coefficient of friction is given? Why?
Static is for when there is no sleep, and kinetic is where there is sleep.
Okay, that is a correct answer. Static is used when the wheel is not sleeping. Okay, let me give an example. Let's take something else, another object. Like for example, you have a platform like this. Okay, and then you have a box lying on this platform like that. If this box is not moving, okay, let's say that this box is not moving, not moving. Then do you think that there is a friction acting on the box if it is not moving, if it is static like this?
Yes.
Yes, okay, that is friction. That's why it is not moving. The friction is acting in this direction, friction, and the weight and everything is acting this way lah. This is mg, this is the na normal force. Okay, when it is not moving, the friction is calculated using mu s times na, the static. That is why it is called coefficient of static friction, because the object is not moving. Once you increase, let's say, the slope angle, maybe like this. Okay, now we have angle like this, and you have the same box, and when the weight of the box has overcome the friction force, then the box will start to move downwards. While the box is moving downwards, there is still friction force. Friction is still acting in this direction. Now let's say the box is now moving. The box is moving down. Okay. And you also have the weight like this, mg, and the normal force, the same force. But now the friction here is mu k times na. Okay, this is the difference. This is the difference. Here mu s, here mu k. So the friction that oppose the motion and the object is not moving, then it is called the coefficient of static friction. While when the object starts to slide down, the friction is still there, but the coefficient of friction that you use is no longer coefficient of static friction, but it is now the coefficient of kinetic friction. Do you understand what I'm explaining here? Do you get it?
Yes, sir.
Boleh faham? Boleh faham? Okay. So not moving is mu s. When the box is sliding, then mu k. Okay, now I will erase this and coming back to our to our problem here. So in our case, we have a object rolling. Let's draw it like this. Okay, so mu s is like our friend said just now. Mu s is for roll without slipping. Without slipping, which means that there is no sliding motion occur. Then you use mu s. Whereas mu k is used for slipping occur. Slipping occur. Okay. So back to our question here. Since both coefficient of friction are given, this problem involve rolling without slipping or slipping. So that is the question here. Why is both coefficient of frictions are given in this question? Anyone? Can you be sure whether this problem involve rolling without slipping or slipping occur? Just by looking at the problem given here. Okay, the answer is no. That's why two coefficient of frictions are given here, because you need to determine whether in this problem slipping occur or not. So our calculation will be slightly different from what we did before, because we need to determine which one is the case here, whether rolls without slipping or the wheel is actually slipping while it rolls. Okay, so I will erase all this and we will start with the calculation. So to calculate this, first we need to assume that no slipping occur. So before we continue, definitely we need to start with drawing the free body diagram. Okay, free body diagram first. So as usual, you will have a weight mg here, and you will have a normal force NA at the contact point. Okay, and you have a torque, which is a moment like this. This is M. And because this is rolling anti-clockwise, in which direction will be the friction? So you're going to have a friction down here. In which direction is the arrow? To the left or to the right?
Left.
To the left. Okay, to the left, because it will oppose the rotation. So now you know rotation is anti-clockwise. So your friction will be pointing to the left like this. Okay, so this will be your friction force. Okay. And then we're going to draw the kinetic diagram. Okay, I will paste the same figure here. Right. So this will be our kinetic diagram. KD. Okay, how many arrows do we have in the kinetic diagram? Is the object moving to the left? We have a left motion here. So there will be an arrow pointing to the left. This will be MAX. All right. And then there is no motion up and down. So there is no MAY. And we have a rotation here. So this is IG times alpha. Right. And our coordinate system in this case, let's define positive X to the left. Okay, following the movement of the object, and positive Y pointing upwards like that. Okay. We will start the calculation with Fx equal to MAX. So now let's calculate Fx equal to MAX. All right, in x-axis, we have the friction. We have the friction force, which is mu times Na, that is the friction force, is equal to 75 kg. M is 75 and Ax is unknown. So we cannot solve it yet because we don't know the value of Na, and mu, we are still unsure which mu to use. Okay, and then we go to the next formula or equation, which is Fy equals to MAY, right? And if you look in the free body diagram, we have Na positive, minus we have Mg negative. So this will be 75 times 9.81 equal to, and if you look at the kinetic diagram, there is no MAY, so this will be equal to 0. So from here, we know that Na, therefore Na is equal to 75 times 9.81. You should get 735.75 Newton. Okay, this is your Na. All right. And then we can use, we can assume first, we can assume that there is no slipping occur. Oh, so before we go to the calculation of friction force, whether to use mu s or mu k, let's calculate the moment first. And in this case, we assume that no slipping occur. So first, assume no slipping. Assume no slipping occur. This is the first step. When we are unsure whether the object is slipping or not, so we assume no slipping occur. So when you assume no slipping occur, it means that down here is the location of IC. Okay, this is only applicable if no slipping occur. That is the location of IC. So to eliminate unknown, we will calculate the moment about IC. So now total MIC is equal to IIC times alpha. Okay. So we need to calculate IIC to do this calculation. So let's calculate IG first. IG is equal to M times kg square, which is 75 times, what is the value of radius of gyration? 375 millimeter. Remember that you need to convert this into meter. So divide it by 1000. You will get 0.375 square. Okay. And therefore the value of IG will be 10.55 kg meter square, right? And when you have the value of IG, then we can calculate IIC using parallel axis theorem. IIC is equal to IG plus M times D square. Remember, D is the distance between IC to G. So basically, this is the D lah. This is the distance D, which is 450 millimeter. Convert to meter, it becomes 0.45 meter. So this will be equal to 10.55. This is the value of IG that we have calculated previously, plus 75 times 0.45 square. Okay, so therefore IIC will be equal to 25.73 kg meter square. So this is the value of IIC. Okay. Now, let's look at the moment about IC. So if we go to the free body diagram, remember the location of IC is now here. This is IC. Okay. So if you cannot imagine which force has moment about IC or not, you can draw a line like I do in the previous class. You draw a line passing through IC, a horizontal line, and also a vertical line and also a horizontal line. So from here you can see that the force that the force that falls on the line will not have moment about that point, about point IC. So in this case, you can see that mg, na, and also the friction, all three forces fall on the line that passes through IC, the vertical line as well as the horizontal line. So the only force that you can see here that has moment about IC is the torque, is the moment lah, is the moment. The moment given here is 150 Newton meters. So in the uh, in the uh, in the equation here, you will write 150 Newton meter, 150, which is the moment. That is the only force that has moment about IC, and it is already a moment, so you do not have to multiply with any distance. Is equal to IIC is 25.73 alpha. Therefore, you can get the value of alpha from here, which is equal to 5.83 radian per second square. Okay. When we assume no slipping occur, it means that AX is equal to alpha times R, right? AX is equal to alpha times R. So we can then calculate AX, which is here, this AX here. We can calculate because we already have the value of alpha. So AX will be equal to 5.83 times R, which is 0.45. So you will get AX is equal to 2.623 meter per second square. This is the value of AX. So this will go here, 2.623. Okay, when we get this value, then we can determine this mu NA. This mu NA. So mu NA will then equal to this mu NA, which is the friction lah. Friction is then equal to 75 times 2.623. Okay, which is 196.8 Newton. Okay, so this is based on assuming that no slipping occur. So to satisfy this equation, we need to check. So for no slipping to occur, friction must be equal to mu S times NA. So let's check whether mu S times NA is the same as what we have calculated, which is 196.8. So mu s here given as 0.2, 0.2, and Na is 735.75, which will give you friction is equal to, what will be the value of friction here? 147.14 Newton. Okay, so you can see here that the friction calculated using mu s is smaller than the friction calculated using the equation here lah, by multiplying with ax, because this ax is only valid if no slipping occur. So I will write down here, since mu s times Na is smaller than the friction calculated up there, is smaller, therefore in this case slipping occur. Okay, so when slipping occur, all the calculation using IC, this IC is no longer valid, so this is not valid anymore. This equation is also not valid, so all this is not valid. So you need to repeat the calculation for the moment. So we cannot use calculation of moment apa ni, about IC lah, because there is no more IC. IC is not valid anymore. Okay, so let's continue on a new page. So what we do here is, now we know that slipping occur. All right. Slipping occur, and therefore AX is not equal to alpha times R, right? AX is not equal to alpha times R. Friction is now mu K times Na, which is mu K is 0.15, and the value of Na we have calculated previously, 735.75. 735.75. So we have the value of friction, which is equal to 0.15 times 735.75, 110.36. This is the actual friction now, because the object is slipping. Okay, so we can go back to the first equation that we have here. This equation, okay, I can copy this to this page. Okay, this is the one that we have. So now this mu is then mu K lah dekat sini. This should be mu K. Okay. So we have already mu K times Na, which is 110.36. Therefore, we can get the value of Ax from here. Therefore, Ax is 110.36 divided by 75. So we have 1.472 meter per second square. So this is the actual value of Ax lah. You can see that the value of Ax here is very different from Ax that we get here, which is 2.623. This is based on the assumption that no slipping occur. But through our calculation, we know that slipping actually occur, and therefore the value of Ax is 1.47 instead of 2.6 that we have calculated previously. Okay. But we still need to calculate the value of alpha. Okay, because the equation requires us to calculate the value of alpha. So now let's do moment about G is equal to IG times alpha, so that we can get the value of alpha. And let's copy this free body diagram so we can visualize the moment that we have about point G. Okay, never mind. I will copy this. Okay, paste it here. All right. So we need to draw the free body diagram again. We have the mg, we have the Na here, and we have the friction down here. So this is mg, this is Na pointing up, this is the friction pointing to the left, and we have the moment. This. All right. So now we want to calculate the moment about G. This is point G. Okay, so we're gonna draw the vertical line along G and also the horizontal line. So you can see from here, mg and Na does not have moment about point G, but the friction has moment. And if we take following the rotation of the object anti-clockwise as positive, so we will have a friction force here as negative lah, because the friction is going that way to point G. Okay, the friction is going in the opposite direction to point G. Okay. So what we're gonna write here is first the moment M, which is positive 150. Is it 150? 150 Newton meter. So it is already a moment. You don't have to multiply with anything. And the friction is negative. So minus, we have the value of friction already, 110.36. Then you multiply with the radius, which is 0.45. All right, is equal to IG. We have determined the value of IG here, which is 10.55, right? So we write here 10.55 and then alpha. Therefore, we can get the value of alpha, which is equal to 9.509 rad per second square. Okay, so that finished the calculation. Okay, any question on this calculation? So in this example is basically when you look at the question, the information whether slipping occur or not is not given, and you can know this by looking at the coefficient of friction given. Two coefficients of frictions are given, mu s and mu k, which means that you need to determine whether slipping occur or not. So you will start your calculation as usual, and by assuming that no slipping occur. So assume no slipping occur, and then you will need to check the friction force. Here you have to compare the friction. Assuming no slipping occur, you will get this friction, 196.8. And by using mu s times Na, you will get another value of friction. And if you see that this value is smaller than this, which means that assumption of no slipping occur is wrong. So you need to repeat your calculation by not using the formula for no slipping lah, which is AX equals to alpha R is no longer valid. And also the moment about IC is also not valid, because when slipping occur, this is not point of IC anymore, because at that contact point, there is velocity, and the value of velocity is not zero. Okay, any question? Any question on the last example of this subtopic? No question? I will share this recording if you want to repeat it again. maybe you miss some information here and there, you can play back the video again and try to understand lah. If anything, you can ask me in the class next week. We will have a normal class next week on Tuesday and also Thursday. Okay, no question on this. This will be the last example problem for this topic before we move on to the next the next chapter. No question? Okay, if there's no question, then that wraps up chapter 2. We have finished chapter 2, which is the planar kinetics, force and acceleration. Okay, and we have covered 3 types of motion: translation, rotation, and also general plane motion. So each types of motion has different way of calculating, although the formulas are almost similar, but the problem requires you to understand how to calculate, and sometimes you need to calculate the moment, you need to use parallel axis theorem, you need to determine where the location of IC and so on. So I hope you can go back and do some revision so that you understand better about all these types of motion, because to me this chapter is not as difficult as chapter 1, so you should try to get more marks from this chapter lah. Okay, so we have finished with this chapter. I think we may have to do a quiz 2 on Tuesday. So we will have quiz 2 on Tuesday. That is coming from this topic lah, this chapter, chapter 2. Okay, let's move on to the next subtopic, the next chapter, which is work and energy. Okay, as you can see here, the next topic is work and energy. And if you look at the rigid body dynamics, what we have discussed so far, this is chapter 1. We learn about kinematics, and we recently finished with chapter 2, which is planar kinetics, force and acceleration. And now we are moving into the work and energy, which is the third chapter of rigid body dynamics. Okay, when you look at the word energy, what do you think a moving object, what type of energy a moving object has? When something is moving, what kind of energy it has?
Kinetic energy.
Kinetic energy, correct. Every object in motion will have kinetic energy. Okay, so this is the first topic in this chapter that we will discuss, which is kinetic energy. Okay, kinetic energy. So kinetic energy is basically the energy a moving object has. A moving object has, right? Every object that is moving, that has motion, will have kinetic energy. Okay. Do you know what is the formula to calculate kinetic energy? The keyword here is moving. Every object that is moving has kinetic energy. So you have learned about kinetic energy previously, maybe in school during your SPM. Kinetic energy. How do you calculate kinetic energy? How do you calculate kinetic energy? What is the formula? Anyone remember? 1/2. Does that ring a bell? 1/2 times apa?
mv square.
Yes, 1/2 mv square. So in dynamics, we will use the symbol T for kinetic energy. Okay, symbol T here is for kinetic energy. So the formula will be T is equal to 1/2 times m times v square. M is the mass lah. M is the mass. V is the velocity. Okay. This is what you have learned before in physics. Okay, so this is one part. But what if the object is also rotating? 1 over 2 mv square is for the linear motion. What about the rotational motion? What about rotational motion? So I will write here that this is translation. This is translational KE, kinetic energy. So translation means if you take a box, for example, the box is moving on the ground from left to right. That is translation. Or the box is drops from top to bottom. That is translation. So what if we have a rotational object? So what do you think the kinetic energy will be? How do you write the formula? We still use the symbol T, okay? 1 over 2. But how do you convert M? This M here, when it becomes rotation, what is the sibling of mass for rotation? Any idea? If the translation is mass, what about rotation? What have you learned in chapter 2? Okay, let's go back to chapter 2. We have F equals to MA. This is the linear. When it comes to rotation, what do we have? F becomes moment. M becomes apa? mg lah ni. This is mg, moment about g. M, what is the sibling of mass? In terms of
IG.
Ig, correct? Mass becomes Ig. What is the sibling of acceleration? A, linear acceleration.
Alpha.
Alpha, correct. Okay. So the same goes for here. So if this is M, what do you think it becomes for rotation?
IG.
Ig. Okay, so this is times Ig. And what about V? V square.
Omega square.
Omega square, correct. So V becomes omega square. So this is the rotational kinetic energy. Okay, rotational kinetic energy. So in dynamics, unlike what you have learned in physics, we have two terms of kinetic energy. So we're going to write the general equation will become T is 1 over 2 mv square plus 1 over 2 ig omega square. This is the general equation to calculate kinetic energy in dynamics of rigid body dynamics. So this will be the general equation. Equation of KE, kinetic energy. Okay, let's zoom into here and focus on the types of motion. So let's say first we have translation motion. Translation only. So if the motion is translation only, does it have omega? What happened to omega if translation only?
Zero.
Omega 0, because there is no rotation. The object is only translation. So then the kinetic energy T will become 1 over 2 mv square only. This is what you learn in physics. In physics, mostly you learn about translation only. So there is no rotational terms. Okay, there is no rotational terms. Okay, so basically this is the This is the translation component. This is the translation. And this is the rotation component. Rotation component. Okay. So for rotation, okay, T will be equal to both 1 over 2 mv square plus 1 over 2 ig omega square. But there is another easier term when it comes to rotation. That is, T can also be calculated about the point of rotation. For example, you have a let's draw something like a rod like this. Oops, sorry. A rod like this. It still become a okay, whatever, tak apalah. Let's draw tebal sikit. Okay, I'm gonna do like this. All right. So this rod is rotating, and this is the point of rotation, point O. Okay, center of gravity is somewhere here. This is point G. Okay, so we can also calculate the this is rotating lah. Katakan dia rotate like this. Okay, this is dia punya omega. Okay. So if we calculate the mass moment of inertia about point O, then rotation punya equation, rotation punya kinetic energy can be simplified into 1 over 2 I O omega square. So you don't have to calculate 1 over 2 mv square plus 1 over 2 ig omega square. Instead, you calculate IO. How do you get the value of IO? Is by using the parallel axis theorem lah. So using parallel axis theorem, you can find the value of IO. So you can use the simpler equation, which is 1 over 2 IO omega square. That is for rotation. And for GPM, for general plane motion, also the same. You have to calculate both because there are both translation and rotation. 1 over 2 mv square plus 1 over 2 ig omega square. And also, if we know the location of IC, then we can calculate the kinetic energy for general plane motion. T is 1 over 2 times IIC times omega square. Okay. So this is basically the formula lah, to calculate the kinetic energy. All right. So the general formula will be 1 over 2 mv square plus 1 over 2 ig omega square. That is the general formula. But based on the types of motion, the formula that you need to use might be different lah, based on whether it is rotation or whether it is translation or general plane motion. Okay. Any question on the formula to calculate kinetic energy before we go into a few example calculation of kinetic energy? Any question on kinetic energy? Okay. If there's no question, let's try to calculate kinetic energies of a few types of object lah, a few objects. Okay, here you can see a disc, a thin circular disc that is rotating, and the fixed point is at the center here lah. This is the fixed point which is point, let's call this as point O, which that is also point G. Okay, let's call this as point G. Okay, so how do you calculate kinetic energy here? Any idea? Which formula should you use? Which formula you should use?
We use IZZ.
IZZ. That is for okay, that is for the mass moment of inertia. Tapi saya tanya kinetic energy punya formula dulu. This one.
Oh,
Yang mana satu you nak guna? Okay, maybe I can copy this and put on the page so that you can choose which one that you can use. Right, let's paste it here. Okay, now we have the list of equations here. Which one can you use to solve this problem? To calculate the kinetic energy of this object? Which one?
rotation.
Okay, this is rotation. So the easiest would be which one? The easiest would be this lah. 1/2 IO omega square, right? Okay, can you calculate IO? Which formula you should use to calculate IO? Before that, let me ask you, where is point O now? Point O is the center of rotation. Where is point O?
At G.
At G, yes. Point O is also point G in this case. So this is also point O. Okay. So how do we calculate IO? IO is equal to, based on this thin circular disc, it is obviously IZZ lah. Betul tak? It's IZZ. Okay, that is point O. So it is 1/2 mr square. So IO is 1/2, M is 100, and R, okay, I think R is missing here. R is 2 meter. 2 meter. R is 2 meter. So let's write here 2 meters. Okay. R is 2 meter. So IO is 1/2 mr square. So this will be 2 square. This will be 2 square. And what do you get from here? 1/2 times 100, that is 50. 50 times 4, that is 200, right? So 200. Oops, sorry. That is 200. So 200 kg meter square, that is IO. And therefore, the kinetic energy T is 1/2 IO omega square is equal to 1/2 times 200 times omega is given here as 3 rad per second. So this thing is currently rotating at 3 radian per second. So you put in here 3 square. All right, so that would be, therefore, T is equal to 900. So what is the unit for kinetic energy? What is the unit for kinetic energy? Anyone? All energy. What is the unit of energy?
Kilogram meters. Meter per second square. Newton per meter.
Newton per meter? No, it's not. The unit for energy is joule. Okay, is joule. Joule is the unit of energy. So all energy lah, kinetic energy, potential energy, all sorts of energy has the unit of joule. So this, when you write down the kinetic energy, T, you write T is equal to 900 joule. All right. So this is the kinetic energy of this disk lah. Okay. Any question on this? Any question? All clear? If clear, then let's move on to the next question. Let me copy the formula first. Okay. Now let's move to this one. Now we have a rod here. Okay. Okay. This is still a rotation problem. Okay. How do you do this? Okay, let's first determine the center of gravity. The center of gravity will be somewhere here. Okay, this is your point G, which has a distance of 3 meters lah. Your point G ni ada distance of 3 meter because the total length of the rod is 6 meter. Okay, this is 3 meters. Okay, so let's try to use this equation first, this long equation, which use both 1 over 2 mv square and also 1 over 2 ig omega square to calculate the kinetic energy. Okay, so let's use that. T is equal to 1 over 2 mv square plus 1 over 2 ig omega square. Okay, now the mass we have, it's 100 kg. Let's look at the V here. Do you know what is the value of velocity V? What is the value of velocity V? From the question.
2.
2 is not velocity. 2 is omega. 2 rad per second is omega. Velocity means the unit must be meter per second. That is velocity. Can you get the velocity when you have the value of omega?
Oh, yes.
Okay,
Omega
V
times
is...
R.
All right, V is equal to omega times R. Now you need to determine what is the value of R. What is R here? R is the distance from where to where? Okay, R is the distance from the center of gravity G to the center of rotation. This is your R. Okay, center of gravity to the center of rotation. So what is the value of R here?
2.
2, are you sure?
3, 1.
1 meter. R is 1 meter. 1 meter. Okay. So then we can get the value of V, which is 2 rad per second times 1, also equal to 2 meter per second. That is our V. Okay, so the first part ni, this part we can calculate already because we have the mass, we have the V. Now the second component is requires us to get the value of Ig. Okay, Ig. So now let's calculate Ig pula. Ig is equal to, for slender rod, remember I said you always use 1 over 12 ml square lah. There's no need for you to check other equation. And straight away go to 1 over 12 ml square. So 1 over 12 ml square, which is 1 over 12 times 100 times L is 6 meters, 6 square. So you will get, what is this? Times 100 times 1,800. Okay, 1,800. 1,800 kg meter square. This is your Ig. Then we can combine to everything. T is now equal to 1 over 2 times 100 times 2 square, this is your V, plus 1 over 2 times 1800 times 2 square, this is your omega. Okay, so you will get T is equal to, what is your value of T? Is equal to 800 joule. 800 joule. All right. I hope you get the same value. Okay. We can also use this equation, 1 over 2 IO omega square, to solve this. Okay, let's try to do that. Let's put a divider here. Okay, what if we want to solve this using T is equal to 1 over 2 IO omega square? So then, now what we need to do is to find the value of IO. IO is equal to IG plus MD square. Okay, IG we already have. IG is 1800 plus M is 100. Now, what is the value of D here? D, as I said, D is the
Sir,
distance. Yes,
yang T itu 3800.
T 3800. Which one?
Yang total T untuk rotation tadi tu. Yang se-highlight 800 tu, jawapan dia 3800.
Iya kah? 3800? Are you sure? Try calculate again. 1 over 2 times 100 times 2 square is 4 plus 1 over 2 times 1800 times 4. Oh ya, yeah. 3800 eh. Dekat mana saya salah? Because the answer is 800. Hmm. 1 over 12. Oh, okay. This is 1 over 12 ni. 1 over 12 kan 1 over 2 kat sini. IG 1 over 12, sorry. So that should be 100 times 6 square and then divided by 12. 300, sorry. Yang ni should be 300. IG is not 1800 but it is 300. 300 kg meter square. Cuba recalculate. Kalau 300 dapat tak? This is 300 here. 1 over 2 times 100 times 4 plus 1 over 2 times 300 times 4. Okay, now you get 800. Okay, kita salah dekat IG. It should be 1 over 12. Tadi saya tertulis 1 over 2. Okay. Okay, thank you for pointing that out. Okay, now let's go back to the alternative formula to calculate, which is 1 over 2 IO omega square. Okay, so now we need to find the value of IO. So IG, we already have the value, which is 300. Okay, IG is 300 plus M is 100. Now D is basically the distance between these two. When you use the parallel axis theorem and you want to calculate IO, the formula is IO equals to IG. So D is basically the distance between O to G. Okay, between O to G. So which is here 1 meter lah. This is point O. Point O is here. Let me use the red color. Point O is basically here, the center of rotation, and the distance from O to G is 1 meter. So in this, you will write 1 square. Okay. So which means IO will give you the value of 400 kg meter square. Okay. So once we have the value of IO, we can go back to this. T is equal to 1 over 2 times 400 times 2 square, which will give you T is also equal to 800 joule. Okay, so you can see that by using both formula will still give you the same answer lah, to calculate the kinetic energy. So you can obviously see that the second formula is way easier, which mean I mean this formula lah, T is equal to 1 over 2 IO omega square, is easier to calculate rather than using the general formula, which is 1 over 2 mv square plus 1 over 2 ig omega square. And you can see from the calculation steps here, this take longer steps, while this take only 3 lines of calculation to get the same value. Okay, any question on the calculation of kinetic energy? Any question? Okay, if there's no question, I think that's all that I would like to share today. So we have basically finished with chapter 2, and I have introduced to you chapter 3, the first subtopic of chapter 3, which is kinetic energy. And next week, Tuesday, we will do a few more calculation of kinetic energy before I go into the calculation of work done, because this chapter 3 is basically work and energy. Okay, if there's no question, thank you for joining the class this morning. I will share the recording in the WhatsApp group as well as in Kalam. Please make sure you watch the recording video again so that you can understand better. Next week, Tuesday, we will have quiz 2, which will come from chapter 2. I will inform further in the WhatsApp group. Okay, if there's no more question, thank you again, and I will see you next week. Right? Assalamualaikum and have a good day.
Waalaikumsalam. Thank you, Dr.
Salam. Good day.